Welcome, class. For this week, we will be talking about the basics about integration. And so one of the first things that we want to make a connection with is how integration is related to differentiation, which is taking the derivatives, all the stuff that we've done before for the past few modules, as well as how all those things are connected together, and the geometric understanding of what's going on with that. So we see here I have four illustrations here, and the first thing that we want to sort of realize is that when we talk about an integral, or the more basic term for it is an antiderivative, what we'll see is that an antiderivative is just the opposite of what a derivative is. So we're going to undo a derivative. And geometrically, what that means is we want to find the area under the curve for whatever function we're dealing with. And so that's sort of the reverse of we want to find out the rate of change of a function in between 2 points, or if we're looking at the derivative exactly at an instant, the rate of change of a function at a particular instant. So from the point where we've studied derivatives up until now, we've been talking about the rate of change of a function either between 2 points and we get an approximation, or we do it at the instant and get an exact calculation. For right now, we want to focus on looking at a function. Instead of studying its rate of change, we want to see the area under the curve. And so that's the illustrations I have here. Now, the way that we go about doing this is we do something called Riemann sums. And so I'll go ahead and write that word out for you here. We say Riemann sums. And so there are several different type of Riemann sums that we can do. We can do left-hand sums, right-hand sums, midpoint, trapezoidal. Don't want to get too bogged down into the theory about that. The main thing that we do want to understand is how we're going to estimate the area under the curve. And so one of the ways that we can do that is we can take different shapes at different sizes and try to stuff it under the curve here. And so the basic choice, or the first choice that we'll use, is a rectangle. And the reason why we use a rectangle is because a rectangle has an easy formula for its area. It's just length times width, okay? Or in this example, height times width. And so the idea here is that we want to try to fit a certain number of rectangles under the particular curve, or around the particular curve, to try to estimate what the area is. And so as you see here with our underestimate here, you'll see that what we've done is we've tried to fit some of these rectangles up under the curve. And so since the function is increasing, what we're actually doing is what's called a left-hand sum here. So, and what that means is that we're saying for this function, and this is y equals x squared, and we're plotting it from 0 to 1. We're saying that we want to estimate the area under this curve by trying to fit 10 rectangles under the curve here. And we do it under by doing the left-hand sum. And so what do I mean by left-hand sum? Well, if we divide up our x-axis here into 10 sections, then you see how this is 0.2, 0.4, 0.6. So in between there would be 0.3, 0.5, 0.7, 0.9. So from 0 to 1, if we divide up this into sections of 10, then we'll see that at each unit or each break here we'll have 0.1 or 1/10. Okay. Now, if we're doing a left-hand sum, what we do is we're taking the function, which in this case is y equals x squared. So we'll say f of x is equal to x squared. Okay. And we're going to plug in values for x starting at x equals 0, and we'll skip for every 10th up until we get to 9/10. So here we'll have it, we'll get the f of x value here at when x is 0, f of x value here when x is 0.1, f of x value here when it's 0.2, f of x value here when it's 0.3, when x is 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. Okay? And so what we're doing here is every time we get that f of x value here at that certain x value, we're trying to find the height of the corresponding triangle. Now, for this particular example here, we said that we wanted to fit 10 rectangles into a space where we have from x from 0 to 10. So that means our width or our difference before we get to another rectangle has to be 1/10. So our width right here would be 1/10. And our height, or f of x, all that depends on where we are. Okay? And so you see we have f of 0, f of 1, f of 0, f of 0.1, f of 0.2, f of 0.3, f of 0.4, so on and so on, till we get to f of 0.9. Now, we've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. Okay? Symbolizing the height of the 10 rectangles we're trying to compare. And so if we do the left-hand sum of that, it would be just the height of the rectangle, which is each of these points here, the y values form, times the width, which would be 0.1 in this case, since we tried to fit 10 rectangles in between 0 to 1 here for the x-axis. Okay? And if we did that, we would end up getting an underestimate in this case. Now, similarly, if we came here for the right-hand sum estimate, this would be an overestimate. And the difference here is that instead of starting at f of 0 right here, we're going to start at f of 0.1 and then go to f of 0.2, f of 0.3, f of 0.4, f of 0.5, so on and so forth, until we get to f of 1. And you see the one point that we left out is the one where we have f of 0. And this is what's called a right-hand sum. And you can see if we were to take the corresponding rectangles for each of these and add up all those areas, it would be an overestimate of the area. Okay? Now, next what I'm going to do is actually write this out so that you can kind of see what this looks like. So if I was going to do a left-hand sum here, then it would look something like this. I'll do a left-hand sum of this function. So I know that every time I'm going to multiply the corresponding height by 0.1, so I'm just going to do 0.1 times, and then this will be f of 0, f of 0.1, f of 0.2, so on and so forth, until we finally get to f of 0.9, okay? And so some of those values here, for f of 0, that would just be 0. F of 0.1 would just be 0.01. F of 0.2 would be 0.04, and so on and so forth until we get to f of 0.9, which would be 0.81. Okay. Now, if we went on and added that up, you would find out that we would get 0.285. Okay. And since we don't really have any units here, we're just going to say that this is going to be 0.285 square units, okay, whatever that might be. And so this would give us an underestimate of what the area is under the curve. Now we're going to go ahead and do the right-hand sum. And so the right-hand sum here would be the overestimate. And so doing this again, our width each time for our rectangle is 0.1. And so we're doing f of x of n times 0.1, or times the d of x here. And so this height times this width here gives us the area of this rectangle. And if we do the distributive property for each of these, you'll see that what we're actually doing here is finding out the areas of each of these rectangles here. Okay, so that's what's going on in case you were not catching on. All right, back to the right-hand sum. So here we have 0.1 times, and so now you see here we started with f of 0, but we don't want to do that now. We want to start with f of 0.1 and skip for every tenth until we get to f of 1. So we start here f of 0.1 plus f of 0.2 plus f of 0.3, so on and so forth, till we get to f of 1. And if you were to work that out, then you would see that this would actually end up being an overestimate here of that amount. Now, just to give you an idea here, we already know what these values are. We know the f of 0.1 is 0.01. We know the f of 0.2 here is 0.04. We know that f of 0.3 is 0.09. And of course, f of 1 would just be 1 because 1 squared is 1. So if we did all that and multiply times 0.1, we would get 0.385, and that would be square units. Okay. Now, it turns out that the exact estimate here is actually 1/3 square units. And we'll see how we get that here in the coming examples. Okay. So this is the first part of studying the theory about the integral of a function, or the area under the curve. In the next example, we'll discuss how to evaluate an indefinite integral and a definite integral. We'll define what that is, and then moving forward, we'll do a few examples.